Okay, we've been talking about linear regression for the last couple of lectures, and today we'll talk a little bit about analysis of variance, commonly referred to as ANOVA, analysis of variance. And this is the basic type of model that we've been working with. We have a response variable, we have an intercept, we have a slope as a function of the independent variable x, and we have these residuals, right? So we don't usually expect in statistics for things to fit perfectly, and so these residuals will tend to be non-zero. And we learned that the least squares procedure, least square error procedure, would go through and choose this line, that is, choose the intercept and the slope for a given set of data, so that the square of these residuals for our data set are as small as sum of squares is as small as possible. Okay, so these were the characters that were involved in that analysis, and there are a couple that we didn't really see yet, but that we didn't define, and that is our sample variance in x, written like this, and our sample variance in sample covariance in x and y, which we can write this way. That allows us to write down the slope in a rather compact form as the covariance over the variance, and the intercept also in a rather simple form in terms of this slope. Okay, so it's important to remember, as I pointed out last time, that every time we collect a new set of data, we will get a different value for the slope and the intercept. And so just like we did for tests on the mean of a proportion or tests on the mean of a distribution, we're going to be able to place confidence intervals and perform hypothesis tests to see whether certain statements will be true or false about the intercept and slope that we get from a particular sample. Okay, so there are a few things that we'll be using. First, this sum of square errors can be compactly written as the number of data points that we have times the average of those squared residuals over all the data points. Okay, so that's sort of a tautomerism that if I add them all up individually, squared, then that's the same as taking the average and multiplying it by the number of them that we have. Okay, so we have a I'm going to go ahead and skip down to the ANOVA section now, and we'll come back to this stuff. Apologize for jumping, but the analysis of variance section now introduces a couple of new players. So this is just this sum of square errors thing, the same thing we just talked about above. It is the sum of those squared residuals. So those are the differences between the line and the data points in this vertical direction. And that gives me this SSE. Now SSR is something new that we haven't seen. It's called the sum of regression squares. And the basic idea here is you find the average of y over your whole data set, and that it would be this horizontal line running across in this direction. And then from every individual value of x that you collected, you take the average of y minus the predicted value of y by this model. That is the difference now, the vertical difference between this average of y and the line at the corresponding point. You square that, and that gives you this sum of regression squares. Okay, so the sum of this SST statistic is the sum of regression squares plus the sum of the residual errors, and you could show that that's the total difference between your data points and your average value of y, right? So this is, in a sense, the total variance of the data as a function of y, right? By definition, that's what we have right here. So this is the total variance in the y variable is related to the sum of regression squares and the sum of the square error for the model. And what we would like to do now is to use the relative values of these two things to tell what fraction is being accounted for by variable x and what fraction is not. That will be related to our r-squared value. It will allow us to assess p-values for these statistics. And this is now a mean regression square, and it's been divided by 1. So you could leave this 1 out in this particular example, but later we will work with distributions that are regression problems that involve multiple variables, and this will no longer be 1. Okay, so it's 1 because we only have the one variable x here in this case. So our mean value for the sum, this residual square, now we're going to divide that by the number of degrees of freedom that we actually had in computing that. So we used 2 degrees of freedom in the beta 0 and the beta 1. So that's n minus 2 in the denominator and not n. Okay, so this ratio, so that is basically an estimate, I should point out, of the variance in my in my data around the model, right? So it's variance around the model and not variance in the whole data set. Okay, so Fisher a long time ago showed that this MSR divided by MSE will follow an F distribution. So this F, so notice that this is a positive quantity and this is a positive quantity. So the F distribution starts here at zero, and it's always has some probability of being non-zero up to the off to the right of 0 along this axis. And the farther away we get, the more important this variable x is in determining the value of y. Okay, so the typical thing that we do with this F distribution is to test the null hypothesis that beta 1 is 0, which is to say that we're testing the hypothesis that variable x has nothing to do with y. The y doesn't depend on x in any way. So the alternative to that hypothesis would be that beta 1 is not equal to 0. And so we can compute this F statistic. So for our data set, the F value is this MSR over MSE. And if we want to test this hypothesis at confidence level 100% times 1 minus alpha, then we can look up in a table the tail values of the area under this distribution going off to the right for different values of alpha, and that corresponds to a different value of this F statistic, right? So in the usual procedure for running these hypothesis tests, we want to find that the degree of confidence that we want gives us a value of alpha that pushes the tail out here so far that our data is actually still to the right of that, right? Does that sort of, hopefully that makes sense. But we're checking to see if our F value in our test is greater than some threshold value that would allow us to conclude that indeed beta 1 is not 0, and therefore that y and x are related to each other. Okay, so there is also a very simple thing that, for example, Excel will put on all of your charts, and that is this coefficient of determination, which is really the square of the correlation coefficient between these two variables. And we can define it in terms of things that we've been talking about now as r squared is equal to 1 minus the sum of the square errors over the sum of the total variance in the variable y, which literally means the fraction of the variability in the data y that is accounted for by the regression model, right? So what we would really like here is for this to go to 1, and that means that essentially all of the variance in my variable y is accounted for when I include y's dependence on x. Okay, so if there's a lot of additional variance, then this value of r squared will be quite small, and that means that x has less and less to do with variable y. Okay, so it's common to go the other direction, I should mention, with this F test and actually report a p-value, right? So for this value f naught, I could look out here on this F distribution with whatever number of degrees of freedom that we have. So remember that we're using beta 0 and beta 1, so it's n minus 2 degrees of freedom, and we're looking at only one variable being important. So this is f naught would appear somewhere along this axis, and I compute the area to the right of that point f naught, and it will tell me for the corresponding F distribution, and that will tell me the p-value, which is the smallest, which is the probability corresponding to the smallest degree of confidence that I could have in rejecting this hypothesis. All right, so let's see an example in Excel where we go through and use the data that we had used some time ago. Remember this little example where we tabulated these numbers x 1 through 5, and these were the corresponding y values. We made this plot. Let's come down now and use the ANOVA feature in Excel. Analysis of variance is something that you can select in Excel. My student did a little demo of this the other day. Hopefully you were in class to see that. So So we have y as a function of x. This is the best fit line that we got. The analysis of variance information is in here. Key things are important. That's the sum of square errors statistic here. This is this mean square error, which is the variance in the y variable, the total variance in the y variable, and so this is now giving you that p-value for the significance of variable x in determining y, right? So this p-value is about 0.035, and that means that we could conclude with 96.5% confidence that beta 1 is not equal to 0. That is, we could reject this hypothesis with quite a large degree of confidence in this case. And so Excel also will give you confidence intervals on beta 0 and on beta 1. Okay, so you see that you have quite a large confidence interval on the beta 0. It could be anywhere from -2 up to 2, and beta 1 can range from 0.1 up to 1.3. Okay, so beta 1 has a seemingly narrow range, but of course these are apples and oranges. Beta 0 is an intercept, and beta 1 is a slope. So these are coming from so-called standard errors in these two quantities. There are t-tests to determine these as well. Maybe I'll give out a handout on that as well, but we will go on from here. So there are a couple things I want to say about confidence intervals on the slope and the intercept. Okay, so it's common to see in textbooks that they'll tell you that beta 1 is within a certain degree of confidence. So we say that we have an alpha level confidence interval on the value of beta 1 being within the value that we estimated from our least squares procedure, and this deviation, right? So plus or minus this t statistic multiplied by our variance divided by our sample variance in x. So this variance in y over the variance in x. And this is our standard error for the beta 0. The corresponding t statistic here gives you a confidence interval on the actual value of beta 0 and how far it might be from the value that we estimated. Okay, so it's important to realize that when we did the analysis of these least square equations, that we solved for beta 0 and beta 1 out of two simultaneous equations. And the reason that that's important is because these two things are interdependent with each other, right? So I should never look at my data with a best fit line that goes through this location and say the largest according to my confidence interval on beta 0 that my intercept could be, so this is the predicted intercept, and maybe the confidence interval goes up to here on that intercept. And I don't want to take this largest possible intercept with the largest possible slope and say that any line in here would be admissible. Likewise, I don't want to say the smallest possible intercept and the smallest possible slope give me another envelope for the lower and upper bound on my best fit line. In fact, when I tend to find errors that lead me towards having a large intercept, I'll get a smaller slope. And when I find a small intercept, I'll tend to find a larger slope. Okay, so that's what I mean by saying that beta 0 and beta 1 are interdependent variables. They're not independent of each other. And it's just important to remember that. So often, rather than looking at pictures like this with confidence intervals on beta 0 and beta 1 considered separately, it's more useful to consider confidence intervals at a specific value of the variable x. Right? So if I look at a specific point along my x-axis, say we look right here at value x naught, I want to be able to say, my best fit model says the value of y at x naught is given by this point right here. What are the upper and lower bounds on that value in terms of confidence intervals at some certain alpha level of confidence? So we can do that. We can say that this is the predicted value, this is the actual value of y at point x naught along my axis is the predicted value plus or minus this t statistic with this standard error, with this alternative standard error that gives me this confidence interval. It actually depends now on which value of x I'm looking at, right? So note that that the center of your data, you always have narrower confidence intervals on the value of y than you do out at the edges. Okay, so as you move out here towards the edges, it becomes more and more like you're extrapolating information whereas in here we're pretty sure.